Okay. So thank you, Yogi. And and I just want, okay, so I'll start by sharing my screen and then we can actually begin. Screen share. Okay, does everybody see the title slide?
Yeah, yeah, it's fine.
Okay, so the subject of our talk for today is a library that I'm the author of. It's not a super cohesive one, so it's called a set of kernel authors tools for CUDA, or CAT for short. There are no cats in the library, and it's just a coincidence that I got these initials. But if somebody has an idea on how to convert an image of a cat into a logo for a library, then I need to think about that too. And you're welcome to make suggestions in the discussion session section of the talk later. Um, so this is my second talk here in this meetup group. And I'll begin like last time with mentioning who the intended audience is. So this time we're talking about writing kernel or device side code. So it's intended for those of us who have some experience writing kernels. It's not introductory, and it will be mostly interesting for people who've actually written or are writing kernel code themselves and don't use other libraries which run on the host side and sort of generate their own kernels. And we will be using some modern C++, or rather C++11. I should mention that the library itself is in C++11. Of course, you can use it with later versions of the standard, but you don't have to use the absolute latest C++17, which CUDA11 supports. And I hope it will stay that way at least for a while. We're not going to have any rocket science or deep template metaprogramming or anything like that. We will have just a little bit of PTX, which is the intermediate representation that CUDA code gets compiled into, but we'll only use it for motivation, so don't worry if you don't know much about PTX. Right, so what will we have in this talk? I'm not going to explicitly discuss my motivation for writing the library. I hope that that through the slides we'll go over, you'll kind of get the idea of why it is that the CUDA KAT exists. I will have a brief comparison with my other library, cuda-api-wrappers, that I mentioned last time, but you don't. It's not necessary for you to have attended the previous talk. And we'll spend most of our time diving into specific kernels, and we'll repeat the process of identifying some issue or something that annoys us or annoys me or some sort of inflexibility. And we'll use one of the tools from the kit or the set of kernel authors tools to change the kernel. And we'll have a look and try to appreciate the resulting code, and we'll repeat this. And then we'll go into a second kernel, or rather not a kernel, but a device-side function, which will be similar to the kinds of functions we have in the algorithm header of C++. And we'll have this similar, we'll not have the process of repeatedly changing it, but we will see a few variants of it, which will, and each of them will use some additional aspect of the CUDA KAT library. I do have some bonus slides, which I will keep secret from now, and it depends, and it depends on whether we have enough time to go over them. And then finally, like Georgi already mentioned, we have a section that's not recorded for questions and answers and discussion of the library or anything related to CUDA or whatever you like, I suppose. So let's get started. So the first way to present this library, CUDA KAT, is to kind of contrast it to my second library, the API wrappers, because they sort of complete each other in some sense. CUDA KAT is strictly for device side code, while the wrapper library was only for host side code. So what things that I found useful that I wanted to share with the community, I kind of separated them along those lines. And it's not, and CUDA KAT is not something that you use in heterogeneous programs. It's really just for when you're writing kernels. And the library itself has 0 kernels in itself. It only has device side functions or context for stuff. And most of the different facilities in CUDA KAT are kind of loosely integrated. That means that you can more or less pick several things or some individual facility that you like and that you think would be useful and not use anything else from it. It's not like some framework that you have to load with a bunch of code that all ties together. The first release of it was last year in 2020, and there's just been a new release. I'm preparing for this talk. It also motivated me to release another version with a few, well, I'd say minor changes. So if you know it from last year, it hasn't changed significantly. CUDA KAT has, I did take the time to write a bunch of unit tests, so I have reasonable, I hope, unit test coverage. It has less users than the wrappers library, which is something I obviously hope to increase, but good few hundred people at least have downloaded it. Not sure, I hope they also use it. It's not a fully baked creation, especially because it's a toolkit. So for example, in this release, I've taken something out because it became broken because of a library dependency on another library, and some of the APIs I'm not entirely sure about, or I'll be glad to get some feedback on. So you could still think of it as a bit half-baked. And as far as size, it's a little under 8,000 lines of code, and there's still a bunch of functionality that I would like to add to it. And the CUDA API wrappers from last time, it's a much more well-baked thing with more users and more people's experience going into kind of fashioning the API. So that's sort of the difference between the two for those who were here last time. Okay, then let's start by looking at some kernel code, and we'll actually whoops, kind of animation glitch. So this is the vector add kernel, and most of you probably know it, both because it comes from the CUDA samples. It's one of the very basic samples that we get with the CUDA toolkit, and it's also so the program surrounding vector add is the program we played with last time with CUDA API wrappers. But now we don't care about the host side stuff. We're only looking at the actual kernel. And if you happen not to know this kernel, what it does, it takes two arrays or two vectors, A and B, and adds up their elements into C in an element-wise fashion. So the ith element of B and the ith element of A are added up and go into the ith element of C. And like I said, we're going to gradually modify this kernel. The first modification is still not using anything from my library, but the first thing I want to do, yeah. So since we're not being very interactive, I'll let you have a few seconds to guess why I asked here about the signature of the function. Um, Forget about my library and anything like that. I just think I should change something in the signature of this function. So what do you think might be missing? So the signature does mark both of its inputs as constant, which is and the output as the output parameter as non-constant pointer. So that's okay. But actually, I want to do a bit of housekeeping in this respect and add the restrict qualifier, which is not proper C++. It's not in the language, but it's actually very useful. It exists in C, and most C++ compilers support it in some way or another. What this guarantees us that, or guarantees the compiler rather, is that there's no aliasing. So the memory that we access through A and B and C are all are disjoint areas of memory. That allows the compiler, and it's particularly true for CUDA, to do certain optimizations that otherwise it's not allowed. And let's also do a bit of renaming as part of this initial housekeeping. I don't really like generic or super generic variable names. So I've taken the first line, which actually gives us the numeric ID of the current thread within the entire grid. And it's a linear grid. So the only a single dimension, the x dimension in this grid, both in the blocks and in the grid of blocks, has more than one value. So in this linear grid, this is the global ID, and I use it below to index the rest of the work. So this is a piece of code that we all see in or write probably in our kernels a zillion times. So the first thing I want to do, and the first thing a library like CUDA KAT does, is do something about this repetition. But before I tell you what I'm doing in CUDA KAT, then let's take a bit of inspiration on this specific change, and that's an inspiration from OpenCL. So we're not going to have an entire discussion about what OpenCL is versus CUDA, but it's another execution ecosystem, you could say, that's also supported on NVIDIA GPUs, but also on other vendors' cards. So AMD supports OpenCL, and you can also run OpenCL on CPUs. And GPU kernels in OpenCL look very similar in many ways to CUDA. So this is the same kernel in an OpenCL version. It looks slightly different. So you may see the fact that it says kernel and not global. But something interesting is that OpenCL does have some built-ins for getting the global ID of the thread. And the reason it has 0 here is because you give it the dimension as an index. So the 0th dimension, or the x dimension in CUDA, you get the global ID, and here's the value that it provides. I could just have lifted this function, but I actually don't like the magic number of the 0. So here is what I do with that in CUDA KAT. So that's the include, or one of the things you include in CUDA KAT. Oh, let me just correct that actually, because it's a CUDA file. Sorry. And there's a namespace for linear grids, and in that namespace, if you use the function thread global ID, it gives you the global ID in a single dimension of your current thread, and then we use that. And there are also some aliases for that identifier. So if you don't remember exactly whether the function is called global ID or ID in grid or something similar, then it's very often the case that the library provides that alias as well. And if you're wondering why I need a namespace for the linear grid, the answer is that if I just use the cat namespace, then it would give me a global ID in 3 dimensions. So we would have to look at the y dimension and z dimension and multiply and add up the values there, which would take even more code. And if you write kernels that are multi-dimensional, then your boilerplate for doing that is even longer. So in this example of the transformation, I added the include directive, but over the next slides, I will actually skip it because we need to fit everything on a single slide. So we just keep it in memory that we also have to actually include things for the cat facilities to work. So about that grid info business. So my basic idea, which also applies to other aspects of CUDA KAT. So instead of computing something about the grid or your position in the grid, then I want to be able to just say it in words, sort of, and then convert the phrase into something that's actually the name of the function. And if you can say it in words, then I've probably implemented it. So here are a few examples. If you want the last ID of the thread in a block. So it's in a block, so the block sub namespace and last thread ID. If you want the overall size of the grid and threads, then you can, okay, it's a grid, so there's the grid sub namespace, and I want the size in threads. I want a position of the thread and globally, then it's global position. So it's not just, then it will be a 3-dimensional structure and not just a number like global ID. And even what's the dimensionality of the grid, or how many dimensions does it have? Is it a 1-dimensional, a 2-dimensional, a 3-dimensional grid? Then I can get the dimensions as a structure with dimensions and threads. And then there's a method that's named dimensionality, and will give you the number of dimensions that are not, that have like a value of more than 1. And a few more examples. And there are like dozens of these. And a lot of these are redundant, but they're redundant to make it easier for you to say basically what you mean rather than write the computation. And a lot of the facilities in CUDA KAT have this intention. So this is obviously, it's not an invention of mine. You have a lot of libraries have at least some aspect of this. But that's basically, so in the transformations we'll see next, this is an element, a recurring element. So less guessing for the right name. Okay, so now let's, the next thing I want to do with this kernel is I want to make it a templated kernel. So I want it to work for different kinds of element types. So obviously it's C++, so we want to use a template. So this is my template. The type name is T, still constant restrict. And suppose it, and that should work, right? And it does work as long as you're doing addition. But what if what you want to do with the two vectors is something different than addition? Suppose we want to use want to compute the distance between the two values. So this is the line of the computation, and I've changed it to abs. Or rather, I'm taking the difference between them and the absolute value of the difference. So is this going to work? If I write this kernel and start instantiating it, or even instantiate it for the float type, which we were using before. And obviously, since I asked this question, then probably the answer is no, it won't work. And this is the error that we would get. It will tell us no instance of the overloaded function abs matches the argument list. So the arguments we have are float. Yeah, not sure why it's float. It's float. It's probably just float. But why isn't there an abs of float? That doesn't really make sense. I mean, float is a pretty basic type, and it said that the abs function is overloaded. So there are some. It's not like CUDA doesn't have it. So when we actually go and look, we see that CUDA follows the style of C. In C, you don't have function overloads, and that means that for the same, essentially the same function, but for different types, you need to use different names. So CUDA has as built-ins, it has abs and fabs, labs, labs, and fabs f. And these are for doubles and long doubles and floats and long ints and just ints. But we want to use this in templated code. So we want a single generic name. And this is something else that cat offers. It takes all of the built-ins. So it has a built-ins namespace. And under that namespace, you have single names that translate into when you, and the template is specialized so that it uses the correct built-in whenever a built-in is available. So if we write this, then this will actually work for floats and doubles and ints and whatever. And wait. So before we go on, I'll again say that that this is not rocket science. These are just simple wrappers, and instead of you having to write them yourself, which you might already have done, now you have them once and for all, and for a bunch of built-ins, including some things that are built-ins but are not necessarily exposed, or things that used to only be available if you used inline PTX and only recently got exposed. So there's a bit more under the hood, but it's just access to what CUDA offers you. Okay, so that was pretty easy, but we're still not all the way where I want to be for templatizing things, because sometimes you have pretty basic functions that you want to have available as templates, but they aren't built-in, so you don't have a built-in for them. Sometimes there are no built-ins at all, and sometimes there are built-ins, but they're only available for some of the types. And I also have some of these in cat. So let's take an example. Sorry, whoops. So the example, okay, we're still with the absolute value example. It turns out that not every type or rather, obviously, not every type that you can think of has an absolute value built-in. Only some of the built-in types. And if you have a custom type of your own, then definitely there's no built-in for it. But we can write a small wrapper, which for the case of built-ins, will actually use the built-ins, and otherwise we'll do this. And what do I mean by this? I'm skipping the tag-based dispatch of the template and other templating voodoo. But essentially, if you have a custom type, then what we're going to do is to and we'll assume that your type, you can compare it with 0, and then maybe if it might be unsigned. If you've declared your type to be unsigned using the std is unsigned trait, then then the absolute value does nothing, and I'll just return your value, and otherwise we'll compare against 0. Now this will not work for any type, but you can. But if you implemented a type which has conversion from 0 and has a greater or equal comparison, then you can use cat absolute value with it, and this will just decay to the built-in when a built-in is available. So that's a further generalization that's useful when you're templating. And so when there's also the case of when you don't have a built-in at all. So that's going to be my next example. And it's log in base 2. So there are actually some built-ins for log in base 2 in CUDA, but only for floating point types. So this is my implementation of log in base 2. And so first of all, it's a lie. This is not the real implementation, but I could implement it if I were to write it in C++17. So in C++17, we can do some compile time conditionals. And if our type is integral, that means we have no built-ins for it. And in that case, what we're doing here, we're counting the number of leading zeros in its binary representation, and we actually subtract that from the maximum number of zeros, and what we get happens to be equal to the log2 of this integral value. So this will work for the integer types, and you can actually see it in the unit tests. The real implementation is in C++11, so it's a bit longer and doesn't use if const expr or is integral v, which are from C++17. But it works just the same, and it translates, and when it compiles, it translates into the same thing, which means that this conditional is only applied at compile time, not at runtime. So at runtime, if you're using it with a float, it will just be the float built in. And if you're using it with an integer, it will just be, actually will probably be find first set and a bit of arithmetic. Right. So that's as far as I want to take it for now with templatization. But it's important to note that if you look at CUDA itself, most of the code that's available to you on the device side is not templated. It's C style, like in the examples that we had. Recently, we've gotten some code that's different. So we have the libq++ initiative of a standard library, or part of a standard library that's usable both on the host side and the device side. But that's kind of big, and maybe if we have time, we'll return to comparing CUDA KAT with that initiative. So like I said, some of the aspects of CUDA are not very template friendly. So one of my goals with CUDA KAT is easing the pain of this templatization. We've talked about wrappers. There are also wrappers around PTX instructions, which are then templated, and the non-built-ins that I mentioned, and also for accessing dynamic shared memory. There is this annoying situation, which I won't go into, that NVIDIA actually provided a solution for. If you want to use dynamic shared memory with templated functions, you might have your compiler might shout at you because there's sort of a clash. So there's I guess you could say a folklore solution that NVIDIA provided, and it's baked into CUDA KAT, and it's even a bit easier. There was also a std cout-like stream, so something you could pipe information to instead of using printf, but I marked it with an asterisk because right now it's broken, because it depends on a certain string library that recent versions of it have a bunch of issues. So this does not exist in the current release, but it will be making an appearance in the hopefully near future. So just to recap, whoops. Yeah, so it's these things which cater specifically to templatization, and other facilities are templated from the get-go. And we'll see another one of those soon. Right, the next and actually final transformation I want to present with the vector add kernel has to do with serializing. I've gone back to addition to make things a bit simpler, and actually I want to break up the statement here into its constituent simpler statements, and there are 7 operations here that you can identify, and here they are. So just going back for a second, it's there is the indexing, which is 3 operations, and then there's we actually need to load the data from B and from A, and we add it up, and then we assign it. So if we break it, we're still in C++. So this is a direct pointer to where I take the element from. The same thing for B and for C. And okay, another correction here. This is the load from memory into something which will hopefully be a register. And this is the addition that's done in between registers. And then finally, we store our result to the element of C that we want to set. And the reason I broke this up because I want to show this to you after partial compilation. So I want to have a look at what this looks like in the PTX that you get when you compile the kernel. So this is, or rather, this is most of the PTX for the kernel. I've removed some stuff from the beginning and the end. This isn't a presentation about how to read PTX, so you might not know exactly what all of these things mean. But 7 of the instructions here correspond to the 7 operations we saw before. So we have 64-bit additions, which are for the addresses. And we have 2 load instructions, which get values from memory. And you'll notice that these loads are of 32-bit floating point type values. We have the addition and addition of the floats, because the other additions were of addresses. We wanted to compute addresses. And then finally, we have a memory store of 32-bit floating point to global memory. And so these are the 7 instructions which do something useful in the loop, but there's everything else in the kernel. So there's a bunch of overhead. The overhead has to do with reading the kernel parameters from constant memory. And we also need to read the special registers which tell us where in the grid we are. And then we have to compute our global ID. And there's also some address-based conversion. So there's a lot of overhead compared to just one proper addition operation. And so the reason I showed you this is to motivate why in a lot of the kernels we write, it often makes sense for us to want to serialize. And by serialization, what I really mean is I want to have a better fraction of effective work to overhead. And for that to happen, I want to work on more elements per each thread. Now this is a bit counterintuitive if you haven't tried this yourself, because why do we want to serialize things? The whole idea of using a GPU is that we want to run things in parallel. But we only get benefit from parallelization to the extent of saturating what the GPU offers, of having every symmetric multiprocessor and every potential thread or warp that multiprocessor can work on in parallel. But the more we parallelize beyond that, the more we just get the overhead that we just saw, and the overhead of switching between warps or blocks. And that's why it does make sense to have individual threads actually serialize some of the work. So here's one way to serialize work while still doing while still working in parallel. And the way I do this here is we have each thread of the entire grid work on a single element and then advance by the size of the entire grid to take its next element. So we're still not using anything additional from CUDA KAT. This is just C++ code. Or I'm sorry, this is information about the grid, which I said we can have. And then we have this loop. So we start with the global ID of the thread, which before was the only thing we worked on. So we had the global ID of the thread, and that's what we used as the index. And now this is just the initial index. And while we can still advance, we advance by the number of threads in the entire grid and continue processing elements in this grid thread. So suppose the grid has 100 blocks of 100 threads, which is not a good size. That means that the size of the entire grid is 10,000 threads, and that means that the thread with global index 1 will first process position 1, and then it will process position 10,001, and then 20,001, until it exceeds the size of the input. So this uses the grid information part. But this pattern of going over linear input at grid stride is also something that recurs at least in my work. And sometimes it's grid stride, and sometimes it's some other kind of stride, like if you want just your block to do some work or just your warp to do some work. But in this example of vector add, we're proceeding in grid stride. And what we can do is convert this regular C-style loop into this. So these are two lines. This is just a namespace shorthand. So actually, it's just the second line that does anything meaningful. And what we're seeing here is a C++ 11 ranged for loop. In a ranged for loop, you have your element, and on the other side of the colon, you have a range. And so this range comes from the namespace cat linear grid ranges, and the range is named grid stride. And it's constructed with a number of elements. And now I'll give you several moments to guess what actually is going on. So how is this grid stride implemented? why can I use this and get the same effect as in the previous slide? And a hint is that pause is just an integer. Okay, so whether you've managed to guess or whether you haven't, the solution that's hiding behind this grid stride construct is a range of integers, which has nothing to do with CUDA. It could actually be a concept in itself. The underlying range of integers could be unrelated to CUDA and just have and it just has the feature of a stride. So you started at some position, and you advance at some integer value, and you advance by a certain fixed number of integers again and again until you reach or until you pass the overall number of elements. But the trick here is that each thread does not use the exact same integer range. So I'll go back to the previous slide. The way the threads in the grid cooperated is they each used the same stride, but each of them started from a different position. And this is just kind of encapsulated into this integer, into this range. So each thread starts this integer range at its global position. So essentially it gets the same effect as with the loop in the previous slide. And the same way we have a grid stride, we can have different kinds of strided ranges, which we'll even see later on. And so this concludes the set of transformations that I wanted to show you for the first kernel. And if I wanted to write a vector add kernel, I would write it basically like this. Actually, maybe even not exactly, because the number of elements might not fit inside an int. But now I'm using two facilities, which I hope I've motivated you to believe that are kind of obvious. And there are not really any fancy tricks behind them. Okay, you could say that an integer range is sort of a trick, but I at least feel that I'm writing less boilerplate than before. And now we'll go on to a second kernel that I want to show you, or rather a second function that I want to show you. Before we actually have a look at that function and explain why I called it warp majority, I want to talk about a concept that you see in CUDA KAT, and I happen to have or to employ in device side code that I write, and that's a concept of a collaboration scope. It's not a concept in the C++ 20 sense. It's a concept like in regular language that we use, not the word concept in formal C++. And this is how I define it. So a function or a CUDA function has a collaboration scope of S if there is a single common effect that you could define for computing that function in all of the threads in scope S. And if we only scheduled the threads in that scope, we would get that effect. So that's a bit abstract. So let me illustrate with a few examples. So if I write a kernel, I consider a kernel to be a grid scope function or a grid collaboration scope. Why? Because the kernel has something that it computes, and like generally at least. And if I schedule all of the threads in that have the scope of the entire grid. So if I schedule all of the threads in the grid, then obviously they will compute whatever it is the kernel wanted to compute. So that's a trivial scope. And another trivial scope is thread scope. So if I write some device function, I can't rely on. I don't know that it involves any collaboration between the threads. And typically, and if it doesn't rely on anything that the other threads do, then I will tend to assume that it has a thread scope, and the only thing I want to do with it is achieve or perform the computation that the thread itself calling the function computes. And anything else isn't something that really exists in code, but it's just a convention or a way to look at the code that we write. And you've already noticed that I have some names, and I use a lot of in CUDA KAT sub namespaces that have to do with things that happen for the entire grid, and or that happen for a block or warp. You already saw a few examples of that with regards to grid info. But you'll also see that for collaborative primitives, or for functions that are part of CUDA KAT that involve collaboration of multiple threads. So like I said, some of the stuff we've already seen from the library has nothing to do with collaboration, and you can just call it in an individual thread, like the log2 or the global ID. But we've already seen that that range that we use for serializing the action on the entire pair of vectors, so that grid stride range, that actually involved the entire grid. And we have different kinds of primitives at the three scopes of grid and block and warp. And and additionally, we have some functions that are similar to what you find in algorithm and in numeric in the standard library, but which work at these scopes. So for a single warp, or actually any warp, but that only regard the warp, or only regard the block, or regard the entire grid. But I should mention, wow, this animation really doesn't work for me today. But all of these are not kernels. So like I said in the beginning, CUDA KAT doesn't have a single kernel that it offers. So now let's go for an example. So I want to implement a function that's similar to the kind of functions we have in algorithm, and we'll see how it's implemented in different scopes. So the function that I'm picking is a function that's similar to COUNTIF from the standard library, but it has a bit of a twist. So here's the semantics of the function I want to implement. We're going to look at a sequence of elements, rather a pointer and a length. And every 32 of these elements, I want to have a majority, look at whether or not each of them satisfies a certain predicate, whether a certain function evaluates the true or false. And then I'm going to take the majority vote on every 32 consecutive elements. And if the majority vote is satisfied or true, then I want to count this warp as one of my warps that has a majority satisfying. So this function is a bit contrived, but we are only writing it as slideware, so don't expect to see this function in CUDA KAT, but it will be useful to illustrate how we can do something like that. it's not a very difficult function to write. We're going to call this function count if warp majority. And the first variant of this function that we're writing is at the warp scope. So its arguments, or its parameters rather, are the data for the current warp, the length of the data, and the predicate. Now, I said that supposedly it works at warp scope, so you might think maybe only a single warp executes it, and the answer is not necessarily. It could be that the entire grid does this, but the point is that each warp collaborates on this computation with, or rather each thread collaborates with the rest of the threads in its warp. So it's going to do something together with the other threads in the warp that does not depend on anything that threads in other warps do. And it's often the case when we write kernels that different warps in our block do different things. And we don't want to rely on the entire block being able to collaborate at once. Sometimes we do. Sometimes we can rely on full block collaboration, and sometimes that's not the case. So we start with the smaller scope, which is just the warp. And if we're going over elements but using just the threads in our warp, before we were able to use a stride of the entire grid size. So if the grid was 10,000 elements, then the stride was of 10,000 elements at a time. Here it's just the full warp, and the size of the warp is warp size, and the warp size is 32. So we're going to go over consecutive elements, but actually each thread will proceed at a stride of warp size, or 32 elements. So what does the single thread do? That's just a namespace, so it does nothing. It has its own count, so this is the thread-specific count. And then it has a loop. If we weren't writing a device function, if we were writing this just on the host side, then the loop would simply go over each element, each consecutive element, apply the predicate, and use that predicate. But here, we have all 32 warp threads having consecutive values for pos, because they start at 0 to 31, and then they advance to 32 to 63, and then to 64 to 95, and so on. And here's what they run. So each of them takes an element of the warp data and applies the predicate to that element, and then it has a true or false value. And then what we want to do is get the majority vote. You could probably, if you've written some kernels before, you can probably implement the majority vote function, because there are some primitives that help us do that. There's a warp ballot primitive that we can use, and that gives you an unsigned integer, and each bit corresponds to a single thread. And then you can count the number of bits. So use a population count on that, and then you can compare the result to half the size of the warp. And if you're at least half the size of the warp, that means that a majority of the warp elements agree, or rather, the majority is true, and otherwise the majority is false. And this is encapsulated in this function. It's a warp collaboration primitive. That's why it's in the warp sub namespace. And we add the result, and the result is 1 if the majority vote is true, and 0 if it's false. And we finish this loop after we've gone over all of the elements. Now, I'm actually assuming that the size of the data is a full number of warps, and not because that's a valid thing to assume, but only because we're writing slideware, and I don't want to go off the end of the slide. So we're making that assumption here. Now, you'll notice that every thread returns the count that it itself has computed. And the reason is that a lot of the times when we work at warp scope, there's free propagation of some values. So the majority vote collaboration primitives lets every lane in the warp or every thread in the warp get the same value. So it's propagation for free. So if everybody has the value for the entire warp, then everybody can compute the count, and we don't have to do some inter-thread communication after we're done with the loop. That means that we actually have the warp count at the end, and not just the count of what's relevant to our thread. So like I said, at the end of this function, it's a device function, not a kernel. Each thread in the warp, or each lane in the warp, has the result for the data that was relevant to this warp. Different warps may have different data, or they may not run the same this function at all. But we're guaranteed that all of the lanes have the same result. So this was the warp variant. Now let's proceed to the case of when we know that the entire block can collaborate on doing this, on computing this count if warp majority. So now we are at block scope. The name of the function is the same. The parameters are basically the same. We have our data, our length, and our predicate. And by the way, I didn't mention that they're all templated. And this is, if you know how the standard library works, you know that it's a very common idiom to have a type name for your function, and then, or function-like object, and then pass it like this. So this could be an object with an operator of like a call operator of parenthesis, or it could be something else that you can apply like this. On the device side, there's less variety in invocable type, so you can't use things like std function. But anyway, that's not our problem. And you can definitely use lambdas. So since CUDA 7, I think lambdas are supported. So like I said, essentially the same parameters as for the warp scope. And here we use a different stride. We already saw the grid stride and the block stride, and here I make another assumption for simplicity about this block. But suppose that the block has size. Its size is warp 32 times 32, or the square of the warp size. And that's the stride value. So if a thread processes position 2, then it will go on to process 1026 and 2050 and so on. The inside of the stride looks pretty similar to what we had before. So we take an element of the data, and remember that the elements in the consecutive threads in a warp look at consecutive elements in the input. And so that's why they can still use the majority vote at the warp level on what they've gotten from the input, and add it up to a count. But now this count will be different for different warps. It will be the same for all of the elements in the same warp, because that's how majority vote works. They'll be different in different warps in the same block. And that means that we need another phase after we compute this loop and we're done with it. We need to share the information that we computed in each of the warps, so that the entire block could use it. So here's the place to put this information. These are the warp counts, and we have one for each warp. And then we use another function from CUDA KAT called share per warp data. And what it does, it uses some scratch space that you've given it. Here, the scratch space is warp counts. It could be in shared memory. It could be in global memory. I don't think it can be anywhere else, but the point is it doesn't care. And this is the this is the value that each of the warp provides. So share per warp data needs to be called by all of the threads in the block. But actually, well, we know that in each of the warps, there's this value, and it's common to everything and all of the threads in the warp. And all of these values are placed in this shared space. And after this is run, we can take the this data that's in shared memory and now apply a warp reduction. We're actually using a sum, and this is the sum of the warp counts we had before. And this is this control flow, or this kind of implementation, is the same implementation you would see for a block reduction or a block sum. Except here, we had this twist with a majority vote, but we could have just summed up the elements themselves, for example. So after summing things up at the warp level, we have warp data. We use this sharing primitive, and then we have a final reduction again at the warp level with information from the other warps. And what we feed into the sum is the value we got from each of the warps. So each lane has its ID. And this is also something from CUDA KAT. This is from cat linear grid lane ID. And that's what we use to index the data here. And then we have another CUDA KAT primitive to do the sum. And I guess I should also mention that the share per warp data, if you look at its template parameters, it has the option of running and synchronizing, or just doing the sharing and not doing the synchronizing. But by default, you get a sync threads in here. And if you want to be like extra careful with wasting time, and you had fewer warps, then instead of these last two lines, you would have to make sure that you would have smaller warp counts, and you'd have to get zeros instead of dereferencing the warp reductions here. That's just the way you would generalize to different kernel sizes. And one last thing I want to mention is the way I implemented this this block scope function is that all of the threads in the block get the correct result, but sometimes you don't need that. So these last two lines, you only need them for when you want the warp to get the result. If you want only one thread in your block to have the result of the COUNTIF majority, because, for example, it's going to write it to global memory later on, then we would not run this for all warps, and that would save a bit of time. But if you want everybody to have the result, then this is what you would do. So this was the block scope, which was obviously somewhat more complicated than the warp scope. And then finally, I want to implement the same function at warp scope. Let's see, how are we doing on time? Okay, so we're a little short on time, and I won't rush it, but that will be the last thing we'll see. And here the signature of the function has changed, because I'm sorry, so now we're at grid scope. We saw it in warp scope and block scope, and now we're doing it at grid scope. And since we're working at grid scope, usually the different blocks in our kernel don't cooperate, don't collaborate. They might say use atomics to work on global memory, which is a sort of collaboration. And we even have it here, but they don't really communicate and wait for each other as a general rule. And that's not always true, because in recent versions of CUDA, it's also possible to do grid level synchronization, but CUDA KAT doesn't support this right now. And also it's not useful for my example. So that means that the output of this variant of the function will be in global memory. So I'm changing the signature. We still have the data, the predicate, and the length like before, but we also have the result. So the result is a non-const pointer to a single value, and that's where I want the entire count if majority result to end up. And here's the implementation. We've gone back to using grid stride like in vector add. And we're doing the same warp level majority vote loop body that we had before. But now the sharing is different. So in the block scope, we had a value for each of the warps, and we wanted to share those, and we shared those through shared memory. We could actually also have used atomics in shared memory if we wanted to. But in global memory, and since we have a single result and we don't have any scratch space, then what we're going to do is just add up the warp results. But we don't want all of the threads in a warp to do this adding up. We only want one lane in each one of the warp to contribute to the global result. So here's another collaboration primitive in CUDA KAT. It's have a single lane compute, which means only a single lane will compute this function, which is obviously a function with side effects, and all of the other lanes do nothing, which is what we usually achieve with if the thread ID modulo the size of the warp is 0 or is some fixed value, then do something. When the effect we want to achieve is this. So this is for achieving the same effect more verbally rather than with a computation. And the function on the inside, so this is a lambda function, and what it does is an atomic add. The reason I don't have the CUDA built-in atomic add is for the exact same reason we saw in the vector add example before. I want to have an add that will work for all of the supported types. So this is a wrapper around the built-ins for atomic add, and this is the address where I'm doing the add, and this is the value. The value here, am I doing this right? No, I'm sorry. This is just, I don't need the multiplication. So I'm adding the, remove the wrong thing. I'm adding my warp count to the global value atomically, which means that all of the warps will be taken into account from the entire grid. And that completes the implementation. So I'm skipping the bonus slides, but maybe we'll have time for them in the discussion. And at this point, I want to thank everybody for sitting through this hour. And I hope I've piqued your interest to maybe try and use CUDA KAT, or at least some of the facilities, because like I said, they're mostly separate. So if you thought that some of what I showed was useless and you don't think you need it, but something else was useful, then you don't have to use all of it together. And like I've shown in the examples, they do work nicely apart from each other. I want to turn things over back to Georgi and to open the talk up for questions and discussion.